Hey everyone, and welcome. Today, we're going to dive deep and pull back the curtain on the magic that's happening inside your computer's operating system, literally right now. We're going to figure out how it juggles everything you throw at it, your code, your music, all those browser tabs, and really see how it all works under the hood.
Have you ever really stopped to think about that? You're there, compiling a huge project. Maybe you've got a lecture streaming, you're chatting with your friends. It feels like your computer is a master multitasker, doing a million things at once. But how? How is that even possible?
Well, here's the secret. It's all a beautifully orchestrated illusion, and the conductor of this whole symphony, that's your operating system, the good old OS. The OS is the mastermind, the puppet master that makes everything look so smooth and so effortless. Okay, so to understand this incredible illusion, we first need to meet the main actors on the stage. Let's start with the most fundamental unit of work in any computer system, the process. So what exactly is a process? Well, to put it simply, it's a program that's actually running. When you double-click an icon to launch an app, you're not just running some code, you're telling the OS, hey, create a process for this. Think of it as the living, breathing version of that static program file sitting on your disk.
Now, a process isn't just on or off. It goes through a whole life cycle, kind of like a journey through these 5 key stages. First, it's started. It's just been created. Then it enters the ready state, where it's basically in line, waiting for its turn on the CPU. Once the OS scheduler gives it the green light, it's running and doing its thing. If it needs to wait for something, like you typing on the keyboard, it goes into the waiting state. And finally, when the job is all done, it's terminated. Simple as that.
You might be wondering, how on earth does the OS keep track of all this for potentially thousands of processes at once? It uses this neat little data structure called the Process Control Block, or PCB. Seriously, just think of it as an ID card for every single process. It holds all the vital stats, its current state, its unique ID, memory details, and this is the really crucial part, something called the program counter. The program counter is like a bookmark in your code. It tells the OS exactly where the process left off, so it can pick right back up again. This little thing is the secret sauce that makes multitasking feel so seamless.
Now, processes are powerful, but creating a new one is what we'd call a heavyweight operation. It takes a bunch of time and resources. So, for all the little tasks that need to happen inside the same application, we have a much more efficient tool. It's time to meet the lighter, faster cousins of processes: threads. The web browser is the perfect example of this. The reason your browser feels so snappy and responsive is all thanks to threads. You could have one thread busy downloading a massive file in the background, while another thread is smoothly rendering the web page you're scrolling through, and maybe a third is playing a video you've hit play on. They're all part of the same browser process, all working together in parallel. That's multi-threading in action.
Okay, so this right here is the absolute key difference you need to get. Processes are totally isolated. They each live in their own separate memory bubble. They can't just reach out and touch another process's data. Threads, on the other hand, all live together inside the same process. They share the same memory. Now, this makes them super fast and efficient because they can easily share information. But, and this is a huge but, this sharing also opens the door to some major problems. You know the saying, sharing is caring, right? Well, in concurrent programming, sharing can be complicated. It's great for efficiency, but it also creates a massive challenge. What happens when 2 or more threads try to change the exact same piece of data at the exact same time? That's when things can go horribly, horribly wrong. This leads to a nightmare scenario called a race condition. Imagine you and your friend are both trying to book the very last seat for a flight online. The system shows one seat left. You both see it, you both click book at almost the same instant. Who gets it? The final outcome is a total gamble. It just depends on whose request hits the server a millisecond earlier. That's a race condition. And in your code, it leads to corrupted data and bugs that are incredibly hard to track down. And this brings us to one of the most famous challenges in computer science, the critical section problem. A critical section is just any chunk of code that accesses or modifies shared data. So the problem is, how do we design our program to guarantee that only one thread can be inside its critical section at any given moment? Any solution that's worth anything has to guarantee 3 things, no exceptions. Number 1, mutual exclusion. That's the easy one, only one process in the critical section at a time. Simple. Number 2, progress. This means if nobody is inside and someone wants to get in, they should be able to. You can't have other processes that aren't even interested block the ones that are. And number 3, bounded wait. There has to be a limit on how long a process has to wait. You can't let it starve and wait forever while others keep cutting in line.
So, how do we actually enforce these rules and stop race conditions from ruining our day? Well, we use a powerful set of tools and techniques that we call synchronization. This is how we bring order to the potential chaos of concurrency. All right, our first tool in the toolbox is the semaphore. The easiest way to think of a binary semaphore is to imagine it's the key to a single-person washroom. If the key is available on the hook, you can take it, go in, and lock the door. If someone else comes along, they see the key is gone, and they have to wait. They can only get in once you come out and put the key back. A counting semaphore is similar, but it's like having a bunch of keys for, say, 5 identical study rooms. Now, semaphores are great, but they can be a little tricky to use correctly. One wrong move, and you've got a bug. So a more modern, higher-level solution is the monitor. You can see from the diagram, a monitor is like a protective shell or a safe. It bundles up the shared data and all the code that's allowed to touch it. By its very design, it automatically ensures only one thread can be running its code at any time. It handles the mutual exclusion for you, making it way safer and easier to work with. So let's just take a step back. We've gone from processes to threads, through the dangers of race conditions, and into the solutions like semaphores and monitors. Why does any of this stuff really truly matter? It's because without these synchronization tools, modern computing as we know it would be completely impossible. It would be total chaos. Every single time you save a document while your music is playing, or every time your multi-core processor does its thing, you are relying on these fundamental concepts to prevent data corruption and ensure everything works reliably. This is the hidden bedrock that our entire digital world is built on. And that brings us to one last big question. The tools we talked about today, semaphores, monitors, they were designed back when a computer with 2 or 4 cores was a big deal. We're now moving towards a future with chips that have hundreds, maybe even thousands of cores. So how are we going to manage that level of concurrency? What does the next evolution of synchronization even look like? That's the challenge for the future. Thanks for tuning in.